Up until this point in this chapter, we've talked about the Cartesian coordinate system, or the XY coordinate system. And so, it's a coordinate system that you're really familiar with. This is the x-axis, this is the y-axis. And sometimes it's more convenient, especially with conic sections, to express them in terms of the polar coordinate system. And so this section is going to be concentrating on converting from rectangular to polar and vice versa. And so this is the Cartesian system. I'm going to bring in a graph that for the polar coordinate system, and that graph looks like this. And so if we look at that polar graph, we can see that we have 0 degrees along the positive x-axis, and then we have, going counterclockwise, all the degrees all the way back up to 360. And so this looks a lot like the unit circle. We'll have to get familiar with 30 degrees being pi over 6 and 60 degrees being pi over 3, and so on and so forth. But I'm going to go ahead and superimpose these two graphs just so we can kind of get used to thinking of one in terms of the other with a good visual picture here of what that means. So if I superimpose them, then if we notice, their centers line up, and what we would call the origin in the Cartesian system is also the origin in the polar system. Where the Cartesian system is, we're talking about, let's kind of split this in half here and talk about Cartesian and polar. Where our Cartesian system is x comma y, our polar system we graph in terms of r comma theta. So in other words, r is a distance that starts at the origin and extends out radially, so extends along one of these degree lines. And then the theta represents what degree line we're extending upon. So the r is going to be that distance, like a distance of 1 on the Cartesian plane would be 1, box, and a distance of 1 on the polar curve would be along that radial line, a distance of 1, so it would be going to this circle that has a radius of 1, or a distance of 2 on a radial line would be going out to the second circle, and so on and so forth. So where the Cartesian system, we have the origin, which is 0 comma 0. The polar system, we still call that the origin, and that is a radius of 0 at an angle of, well, if we have a radius of 0, that means we're here and we're not going out from that point at all. So we could really put in any theta. I'm just going to put a theta in of 0. I mean, 0 and pi over 2 would get us the same point. 0 and 3 pi over 4 would get us the same point. We can have, where we only can express the origin in the Cartesian system one way, we can express the origin in the polar system many ways. And that's true with almost any point in the polar system. And so then the other term then for the origin here is called the pole. So that is that term here. The polar axis, okay, where in the Cartesian system we have two axes. We've got the horizontal axis, we call the x-axis, and the vertical axis, which we call the y-axis. In the polar system, we have what we call the polar axis, and the polar axis is nothing more than the horizontal axis. So this is the polar axis. And then the vertical axis here, I mean, horizontal and vertical still mean the same thing, but the vertical axis, which we call the y-axis in the Cartesian coordinate system, the vertical axis we call the pi over 2 axis, because that's the, radian value pi over 2. And in terms of the polar coordinates, we talked about the polar coordinates there, r comma theta, and then we have these radial lines. So these radial lines are these theta lines here that extend out radially and mark the different angles as we go around the pole, so to speak, or as we go around the origin to set up the polar graph. To convert then from Cartesian to polar, we need to remember a few trigonometric identities. So, for instance, if we would come back up here to the polar graph and we would pick any point, say pick over 1, 2, 3 up 1, 2. So there's a point on the Cartesian plane 3, 2. On the polar plane, what is that those polar coordinates? So in other words, if I were to draw a line here, let's get a good line color, maybe purple. And if I were to draw a line, so that line would be from the pole out to that point. So there is that line. Let me draw that a little bit better. There we go. So from the pole out to that point. So something like that. I'm just going to reposition that a tad. There we go. So that would be our polar. That would be our polar, our radial line there, and that angle would be this angle theta here, and this distance would be some radial distance r. And so if we think about then building that right triangle here, then we have a distance of 3 and a distance of 2, and r happens to be the hypotenuse of that right triangle. So that accounts for this, for the Pythagorean theorem identity there. And then we can get theta by doing opposite over adjacent, so we have our tan theta here to get our angle. And then if we take this triangle and kind of draw it out in general form, where we have r, x, and y, then we can set up our, here's our tangent ratio. The rest of it is just really SOHCAHTOA. So if we look at the rest of these identities, we've got x over r, this is my theta here, measured with the polar axis. Then we have adjacent over hypotenuse, so we have cosine of theta equals adjacent over hypotenuse, so there's my x equals r cosine theta, and sine theta equals opposite over hypotenuse. So there is my y equals r sine theta. And then here's my tangent, and then my Pythagorean theorem. So these are the ways we're going to convert this information. So in that case right there, if we have 3 and 2 and theta here, our value for our radius would be then 3 squared plus 2 squared square root. So 9 and 4 is the square root of 13. So if we think about the square root of 13, that's somewhere between 3 and 4. So if you notice, we're 1, 2, 3, 4 radial lines, so we're somewhere between 3 and 4. And then our theta, so tangent of theta is opposite over adjacent. So we can get that, that radial line then if we do an inverse tangent on that. So if we go ahead then and do our inverse tangent of 2/3. So we're looking at doing a inverse tangent of 2 divided by 3. So we're looking at, I must be in radian mode, so it's, actually let's just keep that, it's 0.588 radians, so 0.588 radians, because that's one way we could express it. And let's just get into degree mode here for a sec. And if I retype in inverse tangent of 2/3, I get 33.7 degrees. So 33.7 degrees. So the Cartesian coordinate 2, 3 transitions then into a radial component of the square root of 13, 0.588, or we could say the square root of 13, 33.7 degrees, as long as we make sure we put the degree symbol there. Minus 2 is really telling us move negative. In other words, if we have to find the 7 pi over 4 radial line. So here's our pi over 4. Here's our 2 pi over 4. Here's our 3 pi over 4. Here's our 4 pi over 4. Here's our 5 pi over 4. Here's our 6 pi over 4, and here's our 7 pi over 4. So if we're looking at going along this radial line, if we move along the 7 pi over 4 radial line, we're moving in the positive direction. So the fact that we have to move in the negative direction really means we have to move out here 2 radial distances. So here is the point -2, 7 pi over 4. And this is what I mentioned a little earlier about the fact that you can list polar coordinates many different ways, because this point is also, if we go along this radial line, which is a 3 pi over 4 radial line, it's +2, 3 pi over 4. So those two mean the same physical distance on the polar graph, which in turn also means the same physical location on the Cartesian graph. If we take a look at this one, we have the square root of 3, pi over 6. So our pi over 6 is right here. That's the same as saying 30 degrees. And the square root of 3 is about 1.7. So looking at that, we're looking at about 1.7, so we're about right there. And so now we're going to go ahead and, in fact, I forgot to convert the other one, but we'll convert this one first. So I'm going to go ahead and draw my right triangle there. Okay, so there's my right triangle. I know this is 1.7, and I know right in here is pi over 6 degrees. So if I want to get my x coordinate, I'm going to set up my r cosine theta. If I want to get my y coordinate, I'm going to set up my r sine theta. So we're talking about square root of 3 times the cosine of pi over 6. Okay, so if you know your exact values for cosine of pi over 6, we know on the unit circle, cosine of pi over 6 is over root 3 over 2 and up a half. So this is the square root of 3 times the square root of 3 over 2, which gives us 3/2. So we are over what? It's about 1.5. If you notice, that's over about 1.5. Our y value then is the square root of 3 times the sine of pi over 6. So that's the square root of 3 times a half. And then knowing these exact values really makes this thing go a lot faster. So that's the square root of 3 over 2. So our Cartesian coordinates is 3/2, the square root of 3 over 2. So this is about, if the square root of 3 is about 1.7, then we're looking at about 0.85, and if you notice, it's just under 1. So this Cartesian point then is 3/2, square root of 3 over 2. Coming back up here, sorry, I didn't finish this one. Looking at this, we'll just quickly convert these. we have our x-coordinate is r cosine theta. So we're talking about an r of -2 and a cosine theta of cosine of 7 pi over 4. Now think about 7 pi over 4, it's right here. And so when we're talking about the cosine of 7 pi over 4, that cosine is a positive number. So we have -2 times the square root of 2 over 2. And that gets us a -√2 for our x-coordinate. So if you notice, it gives us our x-coordinate over here in the negative x values. So the signage all works out if you just carry it through. Y equals r sine theta. So we're looking at square root of 2 times the sine of 7 pi over 4. Now the 7 pi over 4 being this radial line, the sine of 7 pi over 4 is negative. So we have the square root of 2 times negative, I said that wrong. I really said that wrong. Those aren't square roots of 2's there. These are negative 2's. I was getting a little ahead of myself. This is -2 times the sine. So we have a -2 times a negative square root of 2 over 2. And so negative times negative is a positive, so we have a positive square root of 2 here. So we have the Cartesian coordinate systems -√2 comma √2. So left root 2, up root 2. Square root of 2 is about 1.4. So that's looking at about 1.4 over and 1.4 up. Okay, as I mentioned earlier, the polar coordinates, really you can find multiple sets to express the same location on the graph. So here's our Cartesian points 0, 5. So 0 up 5, down 5, 1, 2, 3, 4, 5. So this is the point we're talking about on the Cartesian plane. And so what is that on the polar plane? Well, it's along the 270 line. So we have a radius of 5 in the 3 pi over 2 direction, or 5 in the 270 degree direction. Those wouldn't be two unique points. That would be the same point, just written in terms of radians or degrees. So if we think about going from the pole down to this point, that is moving in the 270 degree direction, which is why this is a +5, because this is actually the direction we're moving. We could also call that -5 comma pi over 2, because if this is the pi over 2 direction, then we can't go in that direction to get down here to this point. We'd have to go in the opposite direction, or moving in the negative radial direction. And that we could also call that -5 comma 90 degrees. Just if you're going to use degrees, make sure you put the degree mark. College Board really prefers you use radians, though, just so that you're kind of aware of that. And then, so what are some other ways we could write that? This is kind of sticking in the unit circle. We could also really, any multiple of 2 pi here is going to work. So really, in a generic term, a lot of times you'll see people write 5 comma 3 pi over 2 plus or minus 2 pi. So we could have 3 pi over 2, we could have 7 pi over 2, we could have 11 pi over 2. 7 pi over 2 would just be doing this and then that again. So that that's kind of the nature of the beast when you're dealing with polar coordinate systems, is that we have this cyclical repeating pattern. And likewise, we could do -5 comma -5 comma pi over 2 plus or minus 2 pi. So we have infinitely many ways we can really describe these the coordinate 0, -5 in using polar coordinates. Same instructions here. Find 2 sets of polar coordinates for -1, 1. So we have the xy coordinates here, -1, 1. So over 1, up 1, we're talking about right there. So we can see that we are along that, I'll call it a 45 degree line. But in reality, it's really 90 plus 45, or 135 degree line. And that's our, if we count by pi's over 4, that's 1 pi over 4, 2 pi over 4, that's 3 pi over 4. So if we're going out in that 3 pi over 4 direction, then we're going out a distance r here. So we have to find that distance r. In the last example, we were going right along a radial line. And that radial line happened to be right along the Cartesian grid lines, so all we had to do was count the boxes. But for this one, since we aren't moving along the Cartesian grid line, we've got to actually calculate the square root of r. So that being the case, let's just do a quick calculation here, or calculate value of r, excuse me. So if we know r squared equals x squared plus y squared, then we're talking about minus 1 squared plus 1 squared. Remember, squaring a negative number, that means a number times itself, so this is actually a positive 1. So we're looking at r squared equals 2, or r equals the square root of 2. R is always a positive distance, so I shouldn't say it's always a positive distance, but when you're calculating this value, we're really talking about the hypotenuse of a triangle, so we'll take the positive square root of that. So the Cartesian, or the polar coordinate then would be the square root of 2 comma 3 pi over 4. We could also call it, if we looked at the 7 pi over 4 line, which goes in this direction, we could also call it along the 7 pi over 4 line, it's negative square root of 2, moving in the opposite direction of that 7 pi over 4 line, which kind of actually, now that I think about it, there are your plus or minus values of the square root of 2. Those are actually two. I said only take the positive, but really you could look at both the positive and the negative root of the square root of 2 if you just adjust the radial answer that you're putting in for the theta. For these three, we're actually graphing now things in polar form. So if we take a look at these, it says graph r equals 2. So if we think about r equaling 2, we can actually, what this is saying is go out a distance of 2. So go out a distance of 2, and then at any angle, really, because there is no restriction on the angle. If they restricted the angle, they would have given us a theta. They would have given us a value for that angle. So if we go out from the pole a distance of 2, that means we're going to that 2 radial concentric circle. We can do that in any direction. We're not restricting the angle. So if we do that enough times, we'll start to see what sort of shape we get, and you probably can already see it start to form as I add points to that shape. We end up getting a conic section, and that conic section ends up being a circle. So when you see the polar equation r equals 2, it's just saying draw a circle with radius of 2. We can see that mathematically if we would just use our Pythagorean theorem here. We know that r squared equals x squared plus y squared. And if r equals 2, then r squared must be 4. And so when we plug in that for our Pythagorean theorem, we see the conic section equation start to emerge in Cartesian form, and then ends up being the equation for a circle. So that's how you kind of convert from a polar expression r equals 2 to a Cartesian expression in terms of x and y. If we take a look at this polar equation, theta equals pi over 3, remember the pi over 3 line is up here at 60 degrees. And so pi over 3 looks like something that is at 60 degrees. And what they're saying really is pick any distance. So in other words, your radius doesn't matter. We can go out to a radius of 1. We can go out along the pi over 3 line to a radius of 1. We can go out to a radius of 2. We can go out to a radius of 3. We can go out to a radius of 4 or 5. In fact, we can go out to a radius of -1 or -2 or -3 or a radius of -4, and so on and so forth in that radial direction. So we end up having then the equation for a line. So the polar expression theta equals pi over 3 ends up being this this linear expression here. So if we think about that, getting that linear expression, then we have to think about going back to those polar expressions, those polar conversions. X equals r cosine theta, y equals r sine theta, and x squared plus y squared equals r squared. And so when we do that, when we do this substitution, we're going to get r squared cosine squared theta plus r squared, oh, excuse me, I'm doing that wrong. So we're gonna look at that, and we're gonna start to convert that into Cartesian form. So we want the x squared and the y squared. So we have to get an expression for r squared, and so looking at that, we then have to kind of try to get this into a linear form. So if we look at then substituting in this value, we get into this first equation, we get x equals r times the cosine of pi over 3, and we get y equals r times the sine of pi over 3. And so we're looking at then, let's see, what's the cosine of pi over 3? Cosine of pi over 3 is a half, and the sine is square root of 3 over 2, so I'm going to go with the r times 1/2. So we're looking at then x equaling r over 2, or in this case 2x equals r. And so I'm going to go ahead and substitute that back in then for this expression. So if I did that, then I would have x squared plus y squared equals 2x squared. And then I'm going to go ahead and simplify this here. So that's equal to 4x squared. And I'm going to bring this over. So I got y squared equals 3x squared. And then I'm going to go ahead and square root. So I get y equals the square root of 3 times x. And so if we look at this, and the reason why I picked the cosine one is because I didn't want to pick the square root of 3 one. If we look at this, this is a line, right, plus 0. So we have an intercept of 0. We have a slope of the square root of 3. So if we go back up and look at this line here, we're going to go over 1 and up about 1.7. And we also know, just kind of a caveat here, we also know that the slope is the tangent of theta, right? And the tangent is the sine of pi over 3 over the cosine of pi over 3. So we're talking about 1/2 divided by root, excuse me, I have that backwards. We're also, then we have sine of pi over 3, which is square root of 3 over 2 divided by a half. So we know that the slope is square root of 3 just by looking at the angle there. So we know we have a slope of pi over 3. Sure enough, we got a slope of pi over 3. So that's the linear conversion for converting that polar equation into Cartesian form. And then this last one, we have r equals secant theta. So we're talking about now graphing this, which is a little more difficult because now we have an r and a theta. So you know when things get kind of complicated like this, the best thing you can do is to start graphing points, kind of like if you would have a Cartesian equation in the form of ax plus by equals c. Sometimes instead of solving it for y and graphing it in slope-intercept form, sometimes it's just easier to make an xy table and start graphing points. So we can make an r theta table here. And remember that secant is 1 over the cosine of theta equals r. So if we made a table here of theta and r, when theta equals 0, that's along the the polar axis here, then cosine of 0 is 1, so we have a radius of 1. So we go from a theta of 0 over 1 concentric circle. I'm going to try to pick some convenient ones here. So for instance, I think I want to pick pi over 3, because pi over 3 is cosine of pi over 3 is 1/2. So if I pick pi over 3 here, then 1 over the cosine of pi over 3 is 1 over 1/2. This ends up being 2. So if we go along the pi over 3 line out 2 circles, 1, 2, we end up right there at that point. And so notice when we go to pi over 2, cosine of pi over 2 is 0. 1 over 0 is undefined. So we can't plot a point for that. If we go, let's go out pi. If we go out pi, cosine of pi is -1. So our radius is a -1. So out in the pi direction, we have to go in the opposite direction of the pi line, which is back over on this point. So that got us another point right there. And if we look at, like, let's see, this is pi over 3. Let's look at, this is 2 pi over 3, 3 pi over 3. Let's look at 4 pi over 3. So if we look at 4 pi over 3, excuse me, not 4 pi over 3, 5 pi over 3. No, that is 4 pi over 3. Yeah, 4 pi, I was right the first time, 4 pi over 3. Then if we look at the value of 4 pi over 3, cosine of 4 pi over 3 is -1/2. And so we're looking at -2. So along that 4 pi over 3 line, that -2 is back at this point. And then if we look at 5 pi over 3, cosine of 5 pi over 3 is 1/2. So that's over there at 2. So along the 5 pi over 3 line, we can go over 1, 2 concentric circles. So if you kind of notice, this is setting up this line right here. And so that line is the x equals 1 line. And we can convert if we just use our x equals our cosine theta. we can convert this nicely because we know r is equal to secant theta. So x equals secant theta times cosine theta. And of course secant theta is 1 over cosine. So we have 1 over cosine theta times cosine theta, which is just 1. So there's our Cartesian coordinate, or Cartesian equation, x equals 1. Okay, so for this one it says convert to a rectangular form and sketch graph r equals -2. So when we're talking about convert, we'll convert this first. So we get x squared plus y squared equals r squared. R squared is a 4, so it's x squared plus y squared equals 4. And so we know that is the equation of a circle and with a radius of 2. So we're talking about basically going out a -2. So if we're at a theta of 0, we're going to go back a -2. And so it just really means go out 2 concentric circles from the pole here, and without any restriction as to what angle you travel on. So we end up getting this circle with a radius of 2 with its center at the origin. Looking at this one, it says sketch the graph r equals 5 cosine theta. So if we're talking about r equals 5 cosine theta and getting that into the rectangular form, then we have to really get substitute out both the r and the cosine theta. And so there's kind of a little, I'm going to call it a trick, but it helps to know that we have this identity that has, based on the SOHCAHTOA, where our x Cartesian coordinate is r cosine theta, and our y Cartesian coordinate is r sine theta. And so if we look at this, really what we're saying is we need an r here to get an r cosine theta. So I can do that real easily. I can just multiply this side by r. It's just that I can only do that as long as I multiply the other side by r as well. So we end up having then r squared equals 5r cosine theta. And we know r cosine theta is just equal to x. So we end up with r squared equals 5x. And r squared, we have our Pythagorean theorem, we know that r squared is x squared plus y squared. So now we've successfully factored out all of the polar references, the r and the theta, and we've gotten our Cartesian reference here. So we have x squared and y squared. We have the same coefficient, so we know it's a circle. The fact that we have this x term out here is just telling us that we have to do completing the square in order to find the center of the circle. So we're going to bring this 5x to the other side, and that's going to give us x squared minus 5x plus y squared equals 0. This does not mean we have a circle of radius 0, because we haven't completed the square yet. And when we complete the square, we'll put a number over here to make this a perfect square, and then we'll put the same number over here to keep the equation balanced. So we will end up with a number over here eventually. The y squared is already a perfect square, so we don't need to complete that square. So for setting ourselves up for completing the square, I'm going to give myself a little space here to get this perfect square for this trinomial. And then I have my y squared, that's already a perfect square, equals 0, and then I'm going to have to add that same number over there. So what is that number? Now we've got to look at this coefficient, and we have to take half of it. So what is half of -5? That's -5 over 2. And then we have to square it. So what is -5 over 2 squared? That is 25 over 4. So we know that this is 25 over 4. And if we add 25 over 4 to the left, then we have to add 25 over 4 to the right to keep the equation balanced. So this written as a perfect square then is just x minus some number. And that number, when squared, has to be 25 over 4. So if you think about that, what number squared is 25 over 4? Well, that's just going back to this number. So all we really have to do is throw that 5 halves into here. We already have the minus sign right there. So there's our perfect square for the x components. Our y, like I said a couple times, it's already a perfect square, and that equals 25 over 4. So here's our equation for our circle. We have a center of h comma k. So we have our circle already set up in standard form. We have x minus. We could have a y minus here. In fact, let me just kind of squeeze that in. We have an x minus 5 halves squared plus we really have a y minus 0 squared here equals 25 over 4. So we have a center at 5 halves. We just pluck out that number. That minus sign stays with the format of the equation. And pluck out this number. There's our center. We have a radius. And our radius is whatever the square root of this is, which is 5 over 2. So 2.5 basically. So we have a center of 5 halves comma 0. So that center, this is Cartesian now, the center is over 2.5, 0. And then we have a radius of 2.5. So we're going to go 2.5 this way. We're going to go 2.5 that way. We're going to go 2.5 this way. We're going to go 2.5 this way. So we're going to set ourselves up for our best possible circle. That's not that good. Let's try that again. Our best possible circle that we could draw. There we go. That's okay. Not my best circle. So there's that circle, and that circle is, if we go back to the original polar equation, 5 cosine theta. So if you might notice then the 5, that's the distance across the circle. The fact that we have a cosine here, you notice how it's lying on the positive x-axis, which is our cosine of theta axis. So a 5 sine theta would be up here, and a minus 5 cosine theta would be over here, and a minus 5 sine theta would be over here. Just to kind of give you a reference to a pattern there.